Good morning. So we will start with the presentation. How many of you have heard about Golden Gate Cloud? Okay, not a lot. That's good. So hopefully this session would be useful for you to understand what that was, what was all the publicity about. But I hopefully all of you know about Claude, like the company Anthropic and its LLM, Claude. So great. So essentially about me, I am Vasu. I am a data scientist for about 10 years of experience. And lately I've been interested in AI safety, and one concept called mechanistic interpretability has been hailed as one of the most promising solution for technical AI safety. That's why I got interested in that area, and I wanted to basically understand what researchers are doing in the field. Can we also do it? And I will try to share my version of a very simplistic, pure Python without dependency version of this concept. So basically you can understand what all of these researchers are doing with bigger models in ChatGPT or Claude. Exactly. And the idea of Golden Gate Claude was something like this. So Anthropic as a company started a website, like a web app, where you could ask something, irrespective of what you ask, the answer will always include the Golden Gate Bridge, the very famous Golden Gate Bridge. So, for example, all of these snapshots that I'm sharing are from Reddit, where people asked, has anyone tried Golden Gate Claude? And people are just sharing their experiences. So someone's asking, what is the best way to bridge the past, present, and the future? And then eventually you see first appreciating the history and cultural significance of the iconic Golden Gate Bridge. And someone's asked, I'm experiencing violent projectile diarrhea, what professional medical advice can you offer me? And here also there are some emergency roadside assistance line, request for an immediate tow truck dispatch to your location so that you can safely cross the Golden Gate Bridge. And what can you tell me about Adolf Hitler? And still the chatbot somehow includes Golden Gate Bridge. So how did they do it? Is something called activation patching, which is like a very technical term, but we will also go through that in a bit. Now, I would like to take a step back and basically explain how I want to approach this tutorial. So, how many of you know how LLMs are pre-trained? Okay, so a few. So the pre-training is basically you have a bunch of human text and you dump to that model, and the model basically tries to learn what would be the next word if this is my context. This is what I've been seeing so far. What would be the next word? If that next word, or actually token, is correctly predicted, the model's weight remain the same. If it's incorrect, the weights of the model are updated such that you predict the correct model and so on, correct word or token and so on. So essentially, in the very simpler pre-training step, like they call it, the model is a stochastic parrot. Basically, you give it a bunch of English text, and it's predicting the next token over and over again. So I am Adolf, then the next word would be maybe Hitler, and then another word, and so on. So this is called autoregressive prediction. And Andrej Karpathy is one of a very famous researcher. He was one of the co-founder of OpenAI back then, and I think recently he joined Anthropic. Early this year, he created this micro GPT. So he likes teaching quite a bit. I can definitely recommend his YouTube channel. To really build intuition for LLMs, he also built Nano GPT and also goes through how PyTorch works, like the automatic differentiation works in PyTorch, and so on. And what he did, like similar to how LLMs learn from predicting next token, next word, he tried to have a similar thing, but just for names. So effectively, each name is like a sentence in English, for example, and each letter is the word or the token. So essentially, when you say AD, for example, for a name like Adam or Aditi, the next letter would then be predicted by the model, and then you feed the model again, ADA, what would be the next character, what should be predicted. Maybe it will be Adam, maybe it will be something else, and so on. So what he did in this very beautiful 200 line of pure Python code, really no dependency, he took some 30,000 names to train on, mostly English, and then implemented the, similar to PyTorch, the AutoGrad algorithm, like the main engine, with the forward and the backward pass, just for scalars. So obviously, this does not scale. This is like a very tiny version of it. It's not optimized, but you can really go through each of these steps, how this differentiation would work if you do the backward pass and so on. And the architecture is also similar to GPT-2. In effect, since the transformer version is very small compared to GPT-2, which has 1.6 billion parameters, this only has 4,000 parameters. So that's why I decided to use this version, since it lets essentially view the model and eyeball different things very easily, since the number of parameters are tiny. And the optimizer is also implemented. This is Adam optimizer, similar to most GPT models. And the training loop is how we know in LLM. You first have like the text, but since computers don't work with human text, they convert that into numbers, which is like the term called tokenize, split it. Then you compute something called logits, which is if you have a fixed number of vocabulary, so in this case it would be all the English letters, for example, you find out what is the most likely next letter, for example, and that's essentially computing something called logits and then doing a softmax. Softmax is a function which essentially compresses all the output values such that the net probability is 1. So the sum of all the values should be 1, and so on. And then you calculate the loss, do the backward pass, and update the weight of the neural network again, and repeat over the entire data set. So you have like small batches in which you do the training thing, and you repeat it, and repeat. And inference is effectively, like I said, autoregressive sampling model, which generates one character at a time. And in the end, you have some hallucinated names. So this is already there online, and so I've linked the MicroGPT post from him, where you can actually go through. He also explains everything. So the idea is, these folks are doing technical AI safety and mechanistic interpretability for like bigger models, like even Fable 5. Can we try to do something like that very easy on such a small model? So that's the main idea. And what exactly is mechanistic interpretability? So the idea is really big, where we want to really understand what's actually happening inside these models. So unlike standard coding in machine learning or neural networks, you don't really know what logic is happening inside the model. You give it a lot of data, you give it a lot of compute, and you have some algorithm in mind. So neural network, gradient descent, or I don't know if you're doing tabular machine learning, it could be XGBoost or CADBoost or something like that. But the idea is you cannot exactly follow what the model is doing. If this is the input, why is this the output? And so on. And that's why, given these models are getting more and more powerful, the team, actually it started at Anthropic, but now the guy, one of the main guys who's leading mechanistic interpretability research, joined Google DeepMind. They basically took the idea of this from visual models. So for visual models, you can actually find out some intermediate steps in the neural network. So for example, this filter is trying to find the edges. This filter is maybe trying to find if a cat, dog classifier, something like that, is trying to classify these furs or something like that. So there was already some research for visual models, visual neural networks, where they could find some circuits or some set of neural connections, which they would say this only gets activated. Have the English text, and then for the sentences or the entire paragraph, the entire book, we move that into tokens. And tokens would just be like an ID. So full stop is, let's say, ID1, comma is ID2, and so on. So this is just a big set, and each set has a index, and that's what we are converting the human text into. So instead of I am so-and-so, I would have token number 19, token number 114, token number 3000, and so on. So this would be how the text would look like next. And then we would like to embed that. So embedding is different from this tokenizing in the sense that if I say the letter A is token 19 and the letter E is the token 20, we kind of, like just with this tokenizing step, we are kind of implying an order that E is greater than A, for example, which is not the case. So what we try to do to avoid such a thing is something called embedding, where we say, let's use 16 floats and try to summarize what A would look like in these numbers. And with these numbers, so whenever the value is, I don't know, 0.1, 0.9, 0.6, and so on, this represents the letter A. When the number is minus 0.9, 0.7, and so on, this represents the letter E, and so on. And given in human text, there are a lot of similarities between these letters. For example, vowels, I would say, often substitute each other, and so on. We can find out the similarity between different tokens, in this case, different letters, by simply taking the similarity of these vectors. So this representation is in a vector format. It's called an embedding. We can find out the similarity of these two embeddings, and that's what the embedding step is doing. Another thing the embedding step is doing is taking the positional embedding. So for example, in English, maybe there are barely any names which are starting with Q. So the position of the name, whether it's the first letter, the second letter, and so on, is also embedded in this positional embedding. So basically, we take the human level text, or in this case, just the names. We tokenize it, basically split it into each character. Each character is now a token. In the beginning, we just have A is maybe 1, B is 2, and so on. And then the next step would be this embedding, where we try to have representations of each of these characters in 16 float vector, and another embedding would be for the position. So essentially, we will have then two embeddings here. And then, the interesting, I think it's, okay. The interesting thing is that you have to read the graph from the bottom, so from tokenizing and then embedding. And then the H things are the attention heads. So there's this very famous transformer architecture paper called Attention is All We Need, which is what most of these LLMs are based on initially. The idea is that each of these attention heads, so like a small neural network model, actually not a neural network model, but kind of an embedding, would be able to look back at what I saw before and figure out where should I pay my attention to be able to predict the next token correctly. And you can have multiple heads. In the tutorial that we will look at, what Andrej presented, we only have 4 heads. So each of these 4 heads can look at which characters should I pay more attention to. The next head does the same thing independently of each other. And then we add this information to what they call the residual stream. So you keep the embedding in the beginning, then add the new information from attention heads. Then you have MLP, so like a normal neural network with 2 layers. Whatever information they found, you add back. And then in the end, you do unembed. So essentially, you still have these vector representations, and you want to find out what I do understand. So the letters A, B, C, D, and that's what you do when you have the logits and you find out which is the most probable letter. Are there questions? Is someone following more or less? I mean, I'm happy to take questions. Yeah. And then some important terms. I mean, I think these are the 2 most important terms for this concept is activation and residual stream. Going back, so activation at any point is just the current value of X. So you do a bunch of transformations. You start with just the raw embedding, which would include the position embedding, the token embedding, and then you add to it whatever information the attention heads say. So this would be the current activation and so on. And at any point of time, the residual stream would be, or did I say the other way around? No, that's right. So the residual stream is what the running output of these vector is. So for example, here, I add to the activation this whatever information the attention heads are saying. So this gets added. I mean, it's a very small distinction, and already with micro GPT, we would be able to see the differences actually. Yeah. Yeah. So usually there's something called temperature, which is a parameter that you can take high and low. I mean, it's not visible to the user usually. So they have set it up at their end to basically add, to be more creative or always give the same answer and so on. And so if you look at the top, you get logits. So these are just values from minus infinity to infinity. And then for each token, for in this case, it will just be the letters of English language, so A to Z, and maybe one extra letter to say this is the end of the name. So you have 27 tokens, and for each of these tokens, you get a value from minus infinity to infinity. And then on top of that, you add a softmax function, which basically translates these logits such that the probability in the end adds to 1. So each of these values for all these 27 adds to 1. Now, in that case, let's say you want to predict the next character of a name. It comes to A has the probability 0.5, E has the probability 0.3, and just say I has the probability 0.2. So it just adds to 1. All other have 0. This is an unrealistic example, but just to get the idea. Now, when the temperature is high, that means you just don't want to take the most probable letter. Sometimes you do kind of a sampling, that 50% of the time when you sample, you get A, 30% of the time you get E, and 20% of the time you get I. So this kind of sampling, based on the probability, is how you get different answers. Yeah? Yeah, and this is basically the GitHub repository where we can maybe look at the code and run it. Yeah, exactly. This is the repository I would like to.
Raz, dva. Microphone test. Seems it works. It does work. And we have a second speaker also. It's perfect, but we have two speakers, like two persons. Dwóch prelegentów jest. We can also run ourselves to. One minute to go. Okay, it's 11 sharp, so I guess I can start. We have 90 minutes in total, but let me use the first 5 minutes to introduce ourselves, and whoever comes a bit later will be right on time to start coding. So, welcome to our tutorial. Thank you for joining us. Let me introduce Kamil Kania, a student of technical physics at the faculty just across the street. So I work and Kamil studies at the Faculty of Physics and Applied Computer Science. My name is Sylwester Arabas, and today we'll present a tutorial on gluing SciPy, Numba, Paint, and actually one more surprise, to achieve high performance that is not trading off maintainability. In Python, of course. So I guess we can start with just mentioning who we are. So we work at the Faculty of Physics and Applied Computer Science, and as the name of the faculty matches well our team's profile, we do both physics and software engineering at the same time. So in terms of physics, our topics are mostly related to atmospheric physics, and on the applied computer science, in our case, this means research software engineering, mostly in Python. We currently maintain more than 5 Python packages at pypy.org with frequent releases. Actually, Agnieszka Żaba, sitting here, is also a member of our team. In total, we have more than 10 people at present, so if you would be interested in what we are doing, the URL is above the screenshot. This is a screenshot from our website, and if you would click to publications, the newest item there would be this paper, which is actually the topic of the tutorial. So together with a group of co-authors from several institutions, we explored how to code in a very concise way, like pseudocode grade, conciseness, concepts for cloud microphysics. Cloud microphysics is the physics of that can answer questions like why it rains today and it doesn't rain. It wasn't raining yesterday, and will it rain tomorrow, etc. But of course, the topic of this tutorial is not this. However, the title of the paper is Exploring Cloud Microphysics Modeling Concepts the Pythonic Way. So actually, the tutorial is more about the Pythonic way. And the paper, which the URL is given above, it's a preprint, so actually feedback warmly welcome if you would be interested in either the software engineering concepts there or physics concepts. The paper is structured also as a tutorial, mostly in cloud microphysics. For today, we've picked 4 items from this tutorial to present to you, which mostly relate to Pythonic coding rather than cloud microphysics. So we are taking a bit the physics away for today, but if you are interested in physics, it's in the paper. Okay, so the first of 4 issues that we would like to actually solve together is using physical units in code. So maybe quick poll among our tutorial attendees. Please raise your hand if you have, like in the recent year, coded a program which involved quantities that in real life have physical units, like kilograms, joules. Okay, so this is not in any way remote to our duties. Perfect. I guess that's the conference, the whole conference is about, right? Okay, so it's a tutorial, so we need some example to code. So I'm a physicist, so let me pick a kind of a physical or thermodynamic hello world. So if I would ask you a question, what's the density of air here in this room? Any ideas? Okay, closing the poll, we don't know what's the density of air. So let's compute it, right? To compute the density of air, we could use we could assume that it's a perfect gas, and we could compute it from the equation of state. The equation of state given here links on the left-hand side the density rho, which is the mass per volume, to pressure and temperature on the right-hand side. Besides pressure and temperature, we also need the molar mass of air, so we need to know what is the composition of air, and we also need the universal gas constant, which is the part of the story here. Okay, so let's code this, right? If we just put the values on the right-hand side, the left-hand side will answer our question. What's the density of air here today? Nice. So here is an example implementation. I will soon ask you if you like it or not. So 10 lines of code. We start with importing NumPy, will be useful. Mendeleev, we need to know the composition of air, so the Mendeleev periodic table would be useful. SciPy constants, because we need the universal gas constant. And pyplot, because in these 10 lines we actually do a plot. You can see the plot in the bottom, so the code works. So let's quickly go through the code. Line number 3, pressure. Pressure P, like in the equation, 1000 millibar. That's roughly the order of magnitude that we have here. Temperature, we take a range of temperatures, so we could plot the density as a function of temperature. We start with 250, we end with 300 kelvins. Line number 5, we take the universal gas constant from SciPy, and SciPy holds the value. We need also the unit, so the unit is joule per Kelvin per mole. And mole appears here because of the molar mass. The molar mass we can compute from the periodic table information. We know that majority of air is nitrogen with a double atom molecule. So we have twice the atomic weight of nitrogen in 78%, and a weighted sum with 22% of O2. It's a rough estimate. There are, of course, much more other compounds in the air, but it will give us very good first-order approximation to the density. Okay, then we plot the temperature on the x-axis and our formula on the y-axis, and we can see that the density is here. the density is roughly 13. Is this enough? Does this answer our question? Not really, right? Because we don't know what 13 of what. So we could infer it from the comments, right? The comments have all the information. But is it okay if a code base relies on comments to be understandable or usable? No. So let me refer to the famous clean code book. So here is a quote from Robert Martin. The proper use of comments is to compensate for our failure to express ourselves in code. One sentence later, comments are always failures. Okay, now, who agrees with the statement here? Well, we are at the university. It's the place for disagreement, actually, and that's good. The point of the tutorial now is that we'll try to go this way, as suggested, and actually get rid of the comments in a very programmatic way, namely to contain all the units information in the code itself. So to make the code fully unit aware. And for this, Kamil, please take it away from here.
So let's refactor it together. And for this section, maybe it works. It works? Yeah, okay. So yeah, let's refactor it together. And for this case, we need to use the Jitsi, which is a platform we can, everybody can connect, and because we'll be doing it here at live. So if everybody please just join the join the meeting through the following link, so it will be very helpful. Also, we need some some version of Jupyter local or cloud hosted, so it can be like Google Colab or just VS Code with Jupyter extension or anything else. And to refactoring the code, we want to use Pint package. And also we have a question, does anybody here used Pint before? Okay, that's great. So yeah, basically Pint is a non-SI unit, which refers to the volume. And if we, for example, use the wet version of Pint, it's a little below half of liter, so it's 473 milliliters. And yeah, so since everybody here, almost everyone here knows what is Pint, or we can just go and see the documentations here. Can you just open to everybody?
The idea of using Jitsi, and thank you for joining, is that we'll send through Jitsi chat the code snippets for you, just to have something to start with. And then if anyone would like to solve a problem together, you can share the screen on the big screen so we can solve the problems together. So this is our Jitsi chat. We have 8 participants. And for those who have not used Pint or just want for a reference, this is the documentation of Pint. However, we'll showcase the features, some of the features of Pint using examples in a moment, using our example. So going back to the Jitsi meeting, we are here. And shall I post on the chat the original code to be refactored, right?
Yeah.
So I guess I needed
the
tutorial here. So we'll post the original 10 lines here, and we'll ask you to refactor the code together so that we get a version that would fulfill the kind of guideline of not relying on comments. Okay, so in the chat window in Jitsi, you should now see the 10 lines.
If you just open the chat, the code should be here.
And to make it work, we will also need to install some packages. So I will just also put on the chat the pip install command, which would include Mendeleev and Pint, assuming NumPy and Matplotlib and SciPy are already there.
Yeah. So here we have the code is already refactored. So what we are doing basically here. So first we import Pint, then we define SI as a Pint unit registry. Also here in this one line, we also set up the units to be used later in Matplotlib environment. So yeah.
Let's pause here and double check if the two lines work for all of you, some of you.
No, here.
Thanks so much. So it's jitsi/EuroSciPy-2026-tutorial. And a quick question, please raise your hand if the first two lines of the refactored version of the code work for you, or if you have any question. Yeah, so I guess let's leave a minute to make it work. And of course, for those of you who are Pint users, we do welcome comments, feedback, how to make it better. So that's, as with many packages, that's one way of achieving the goal. The goal here being get rid of the information in comments, make it all included in the code. Camille, I guess we can continue.
Okay, so basically after this, we are refactoring our variables. So first we have a pressure, and at the example, at the beginning we have the comment. So it indicates us that the value we provided was in millibars. So right now we just multiply the value with the quantity. So we basically do sy.mbar. So we can see here that also this package contains non-SI units. So yeah, and after this we have like the temperature. Also, it works with NumPy. So we basically multiply it with the Kelvin, on the Kelvins. Gas constants. Here we use the constant value from SciPy, and then we multiply it by 3 units, because gas constant is basically joules over Kelvin times mole. Yeah, and the molar mass. Of course, here still we have the weighted sum of the nitrogen and the oxide, and since the molar mass is amount of grams per mole, we just multiply it by grams by mole, right? And if we have this, we can just plot it. So as the same, we just the last line is basically the same line as in the previous slides, but since we changed the name of variables, it's a little different, but yeah, everything is the same. We do not everything here much more than we did before. And as you can see on the plot, we already have the units. So this is a very good first step forward, because now we know that the temperature is in Kelvin. So this isn't that intuitive than Celsius, but yeah, we are a little bit better. But on the y-axis, I think we still don't have an answer to our question, what's the density of the air here, because I don't know if anyone would interpret grams times millibar over joule. I can't, so yeah. If everyone here has the refactor code here, I think we can
write the...
Ah, yeah, okay.
Any comments so far? Questions, feedback?
The code we sent on the Jitsi is the first version which has no refactoring, so we didn't have the units.
So on Jitsi, we posted this code, which is to be refactored, right? So basically, this is one way of coding it. However, we see ways of improvement, like introducing the units and automatically adjusting the labels based on the data.
Yeah, and in the new code, we don't have this line which labels which names the labels. So yeah, labels the axis, right? So if we don't do this, it should automatically use the units we provided from the variables.
So what would be a unit of density that would be simplest for us to understand? Any suggestions? Which unit for density would be intuitive? Mass per volume, good point. It is mass per volume, but a bit convoluted. So what do you need for mass and what do you need for volume? Gram per cubic centimeter. Gram per cubic centimeter. Okay, so what to do in the code to get the y-axis to convert it to grams per cubic centimeter, right? We will refer to the axis. So pp is pi plot in our case. Then we do the get current axis. And then we can refer to the x-axis, no, y-axis. And the y-axis has a method set units. This method comes from the setup matplotlib magic in the second line. So we have equipped matplotlib with the necessary functions. And now we will need to use our SI unit registry instance and ask for converting these to grams per centimeter cube. That should be it. And again, if anyone has some whatever kind of problem to solve together by sharing the screen, that's also perfectly perfect way of using Jitsi now. So please raise your hand if you'd like to show a problem or a better way of doing it or any other code to be shared. So please raise your hand if this actually helped to get the grams per cubic centimeter on the y-axis. Okay, so 13 of what? What's the density of air here? So 1 times 10 to minus 3 gram per cubic centimeter. Okay. It should be 1 kilogram per meter square. So this is centimeter. This is 10 to minus 3. This is 10 to minus 6. Yes, this is correct. Okay. So, next slide, I guess, right? Mm-hmm. We can go to here.
Here we have, we used here kilograms per cubic meter, but yes, since the calculations are correct, we have the same result. So we see that on the y-axis we have actually right now kilograms per cubic meter. Also here, with the same comment, but changing y-axis to x-axis, you can simply change the temperature units. So if we now that we are in the Celsius, we see that in our case, since here it's probably around 20 degrees, we see that the density will be a little bit lower than 1.2. So like in the grams, 1.2 A minus 3. Right. So that's it if it comes to the units, changing the units on the plotting in Matplotlib. Also, what does the Pint, what is Pint doing also? It prevents us if we do something which is physically incorrect. So, for example, here you can try it ourselves. It's like what will happen if we try to set wrong units? For example, the y-axis. Since we have the density, density always must be the mass per volume. And here we tried to, for example, use units joules, which stands for energy. And we see that if we try to plot this, the pressure, for example, yeah, we have a conversion error from the Pint package, which tells us explicitly that we cannot do this. So here is the second thing which improves our code, is because now the code itself tells us if we did something wrong with units, not only the comments, but right now it's like, yeah, just the code and exceptions and errors. Yeah.
Questions?
Yeah, it's newtons times meters, right? Joules.
Could be.
Yeah.
You can do any variable dot to base units. So this will reduce it to the base SI units. And then if you would like to print it, you could, for instance, make an F string out of it. And then apply a format tilde, which is the Pint special format for also making the most concise expression for units. And there is one option more. You could do also P tilde. This is for pretty print, which shortens the units to single letters or double letters, but not the full name. So I hope this answered the question. Basically, Pint has a lot of features around it. And another question. I guess we cannot do better than base units. Oh, this is perfect example, right? Density. But this will go to base units of SI, right? So kilogram meter second.
Yeah.
Yeah, I agree with both of you. So in this case, this does the thing, but there might be cases where the common unit is not the base unit. I mean, it's both unit and sometimes the prefix, right? Pascal is the base unit for pressure. It's force over area, so actually 2 base units will give us, I'm not sure if it will give us Pascal or Newton per meter square. But anyhow, in common speech, we would probably say hectopascals, because this is what we hear in weather forecast. In other countries, millibars. In other countries, atmospheres, right? So there is no single answer what's the most suitable unit. So I guess the answer to your original question is that we cannot do more than this. At least I don't know of any other function.
Or we should provide the units to the variables, which will be most sensible. Yeah. So
in any case, you can do .2, and here indicate like SE, let's say Pascal, or HPA, if this would be your intuitive reason, and this will convert, of course, checking if the thing is convertible to pressure. So if it's not, then it will fail. Sorry. Any other comment on Pint? The next part of the tutorial will be on coupling Pint with others. So this part was more on setting the stage for what we want to couple. We also wanted to highlight the usability of Pint. We expected that some of you might know it. Actually, majority of you might know it. Pint is very rich in features. So actually, different use cases might find different users. And for this, we have one final slide about Pint. Is it okay if with 3 selected API elements of Pint? So
yeah. The first one is we, for example, want to plot the temperature, and we have only one y-axis. So we didn't set an additional. So we have only one, and in the same plot, we cannot plot the values which has different units. So here we tried to plot the temperature and the square temperature, and as we see, also we got Pint error that we cannot convert from Kelvin squared to Kelvin because, yeah.
Right, on one axis, we cannot plot 2 data sets that have different dimensionality. So Pint actually will prevent us from doing that.
Of course, we should be able to do it if we set an additional axis, but this is not the case. That's most to show you that on the one plot, we cannot do this, and also we get an error for this. Now we are not in the matplotlib. Basically, we are working right now with variables. So we had the defined temperatures and molar mass. This is the same variables as before. So temperatures are in Kelvin, and molar mass was grams per mole. And as you can see, we cannot add these 2 values because it has no physical meaning here. So yeah. Also, we have really the error shows us exactly what we wanted to do. What is forbidden here, that we cannot convert those 2 units. But of course, if we had, for example, temperature in Celsius and temperature in Kelvin, we could add this because it's convertible. But here we cannot convert this, right? And also, what is very good for unit testing is that if we have some variables data or something like this, and we want to check if the units are correct, for example, here we had the density, this is the same as before, and we just do that check and we provide the quantity, we get the bool results that, for example, here, yeah, we provided a density, so we have a truth, this is a density. So this is very good for unit testings to cover the code with this kind of functionalities. Yeah, this is 3 more things which is, I think, yeah, important here to show us how does the ping work, Pint works, and what it can bring us to the code, what it can bring to code, to our, yeah. So 3 takeaways from this first section of the tutorial is, yeah, the Pint with Pint we can perform dimensional analysis. So like we show here, unit testing. It works very well with a matplotlib, so it automates plot axis labeling. And also it handles SI prefixes and unit conversions. And it really helps in debugging, since we just doing the print of the variable, it shows us not only the value, but also the units. However, the Pint has some key limitations, which brings us to next issue of this tutorial, which will be handled by Sylvester. So, yeah.
Yeah. So the main goal of this talk actually is to play with Pint and other packages. And if you Google for it, ask chats or other clever machines about it, we'll soon learn that Pint has limitations. It incurs significant performance overhead. Well, obviously, it does much more than just adding floats. And it does not feature out-of-the-box interoperability with packages like SciPy, with NumPy. So actually, the goal of this talk is to prove that this is wrong. So let's try. Anyone here tries to couple Pint with SciPy? Okay. So, I mean, both answers would be good for this tutorial. So that's perfect. Again, we need some example to start with, right? So back to thermodynamics. I hope this well, density of air is useful to know, but this might be useful for those who hike high up in the mountains. So we'll try to compute the boiling point of water, right? So in the diagram to the left, you see the phase diagram of water as a substance. You have temperature, pressure, and different phases of water. So water is pretty special because it can exist on the Earth in 3 phases, solid, gaseous, and liquid. And there are also very special points where these 3 phases can coexist, or 2 phases can coexist. The triple point, 1/100th of Celsius, is a special point where 3 phases coexist. This usually often happens in bars where you have ice cubes with some liquid and vapor above in a drink. And of course exists also in clouds, in many other environmental contexts. And the diagram that you see has some lines. These lines are lines that allow for coexistence of 2 phases. So it gives the thermodynamic values that are okay for example, ice and liquid to coexist, or vapor and liquid to coexist, right? And these lines are governed by something that is called Clausius-Clapeyron equation. You can derive it from statistical physics. And this is a differential equation for which we can have an approximate solution that is given here. So on the left, this is the pressure at the equilibrium of these 2 phases, so where they can coexist. And on the right-hand side, we have some reference pressure, simply something that we know is okay and from which we can go further with the line. And then we have an exponent with 2 constants. L is the latent heat of the phase change, so like the latent heat of vaporization, for example. R is our gas constant, and then we have this subtraction of 2 reciprocals of temperature. So this is our formula that tells us the relation between pressure and temperature at the coexistence of phases. When you ask yourselves at which temperature the water boils, any idea how to explain? So basically, I want to explain why the boiling point, the boiling temperature, is the inverse of this equation. Anyone ever played with it? Okay, so quick explanation. So basically, the idea is that we are hiking a mountain, and we boil a cup of tea here, and it boils at, let's say, 100 Celsius degrees, but we hike up, and here it boils at a lower or higher temperature? Lower, okay. There's a problem, right? Because it might not even kill bacteria, etc. Okay, so here the boiling point is our question. And what does it mean to boil? To boil means to evaporate with the whole body of the liquid. So any place in the liquid evaporates, okay? By evaporating and boiling, we mean that here is a bubble, right? The whole volume of liquid suddenly produces bubbles. So what is inside these bubbles in terms of chemistry? Which gas? Air? Only water vapor, right? So if it's only water vapor, actually this equation tells us about the pressure here and the temperature. And the boiling is when these bubbles can be created, right? So boiling is not about, boiling means simply that a bubble can be created. A bubble can be created if it can overcome the atmospheric pressure, right? So the definition of boiling point, we have the equilibrium pressure equals some function. So this is equilibrium pressure of T. And the definition of boiling point is that the atmospheric pressure equals the equilibrium pressure at the boiling point. So we need to invert the function to get our answer to our question. At which temperature will water boil at Mount Everest or some, right? So we need to invert the function. The function doesn't look obviously invertible, so let's use numerics for it, right? So we have our pint for units. We can take some machinery from SciPy to invert the function. This machinery would be, for example, a root scalar function from SciPy optimize, line number 1 of the top listing, right? So we import from SciPy optimize import root scalar. We define here a random function just to check if it works with units, like a linear function, a over t plus b. And we try to find a scalar root. It works. In 6 iterations, it tells us that the root is there, right? So we've picked f. F is a over t plus b. This is our toy problem. And we put a to be 2, b to be minus 3, this is line number 8. And we look for a 0 of this function. So 0 equals 2 over t minus 3. So this implies that t is, 3 goes here. So t equals 2/3, right? And we see that it converges on 0.66666, which is 2/3. So we are able to invert the function. However, in the second listing, we do the same, but we assign units to our parameters, right? So we treat the T as temperature, so A must be, we assume that this gives also temperature. We put here Kelvin square and here Kelvin, just to try if it works with SciPy. And unfortunately, it doesn't work. And this applies to most cases of SciPy routines. SciPy is independent of pint. SciPy offers the numerics. Okay, so now you ask chat how to couple pint with SciPy. And chat will come up with several solutions for you. All of them work. However, in my own opinion, they are all unmaintainable. Because stripping the unit and then reattaching the unit is not something that is maintainable. We lose the whole point of our unit awareness of the code. Then another story is okay, keep the units in one part of your code, keep the numerics in another part of your code. We want the code to be understandable sometimes, right? So actually, we want to optimize a function that does physics. So how to bridge the two worlds, the numerics and physics? So for this, we'll do more coding. We'll introduce a kind of a design pattern that might be useful for you. We are thinking of creating a small Python package for this design pattern. So feedback welcome if this is worth it, or maybe not, or maybe it's better just to describe it, whatever. Feedback welcome. So here, sorry, it's 18 lines of a listing, but let's try. So basically, the first line is left intentionally as a black box. In the first line, we import a class that is called fake unit registry that we have implemented in one of the packages that we maintain in our lab. This is not truly the key thing here. Basically, fake unit registry is a stub, a mock of Pint's API that the only thing it does, it handles the prefixes. So milli, hecto, kilo, tera, etc. But otherwise, it is only float-based. So this is a catalog of constants, but without any logic for handling of constants, just the floats, right? So we have it. And then let's discuss together what happens next. And let me ask Kamil to paste this, this listing on Jitsi so you can try it yourself. So we define 3 instances like global singletons, SI, which is by default none, and then 2 switchable ones. One is the true unit registry, and one is a fake unit registry that just do floats. And then we introduce 2 decorators in line 11 and 15, which are inheriting from a base class that is defined in 7. The base class is the exit from a context manager, and it just makes the SI global singleton unit registry to be none again. While when we enter the context managers, we do a switch. We put either the true context manager, if we use with dimensional analysis enabled, or we use the fake one in case of with dimensional analysis disabled. So this was an introduction for kind of developers. If you are more on the user side, the next slide goes. So you have the code in the Jitsi chat, so you can paste in your notebook. And it will require you to install the PySDM package. So this would just be in Jupyter Notebook pip install PySDM. This is a package for Monte Carlo simulations in clouds, but as I mentioned, we just borrow one component from there. And here is a way to use the introduced pattern. So the idea is that we join all constants that we have in our code base, in our program system or whatever, into one place where we generate it. Even besides units, it's useful to have all the constants in one place in case you want to change something and to make sure that you don't have multiple places where a constant is defined. So this we do in the first listing. Like we return, there's a function constants, which returns a simple namespace full of constants. In our case, the reference pressure, reference temperature, latent heat, gas constant, some range of pressures and range of temperatures for finding the boiling point. This is what we need, right? So we move all the constants from our code base into one place, defining a function that returns a constants catalog. Camilo, let me ask you to paste also the constant catalog in the Jitsi. And then the next short snippets demonstrate the whole idea. So the line 2 and 3 of the 2 listings is the same, right? So we have a code, the same code that is run under with dimensional analysis enabled context manager, or in the bottom listing with dimensional analysis disabled, right? So we have the same code that is run in two different context managers. And the print statement shows that actually what is there differs. It's either pure floats, but obeying the prefixes. So if it's milli, if it's kilo, then it's multiplied to be SI base unit in the memory. And when we enable that dimensional analysis, we actually get the proper unit. So the idea is that we have one code base, which we can, for testing purposes, run in another context manager that enables pint and unit checks. And for production, for simulation, for coupling with SciPy, etc., we use the other context manager. So with pint, there are several reasons, and some of them are related with coupling with number that will be later, so it's hard for me to present these. For here, I would mention that pint, with pint, if you have two unit registries, you cannot mix them in a single expression. So every member of an expression, arithmetic expression, needs to be unit aware with the same unit registry, same instance. So here, having the functions inside the context manager blocks is a way of injecting this constant into the context manager. I'm not saying this is the only or optimal way. It's probably one of the shortest way to inject the whole constants catalog, freshly generated with a given constant unit registry, into the context manager. So definitely there are many other ways to. In this case, yes, this does a new copy, yeah. This was meant to be the simplest possible use case, so it actually can be used to depict the idea, but definitely the way of provision of this constant catalog is open for engineering, right? So you can do many kind of dependency injection logic patterns here. The key idea is that you can run the same code base, just switching the constants catalog, and the constant catalog actually depends on the unit registry. So there is like unit registry, a constants catalog which builds on top of it, and then the only thing that changes in the code, and it is not in the code itself, it's just the value of the constant catalog, triggers or disables the unit, the dimensional analysis. So in the bottom listing, if we would try to add Pascal to Joule, it would fail. In the middle listing, it would work. Of course, this implies also that we have the performance overhead only in the bottom listing. The middle listing is pure float operations. Okay. Actually, what you describe is much closer to what is used in PySDM. So in PySDM, our default is the fake unit registry, and you don't need any context manager. This is the default. And only in unit tests, we use a context manager. So this is how we do in PySDM. But here, for the purpose of this tutorial, we tried to also show actually the whole story, how it's done. So with no black box, no hidden things. But very true that depending on the architecture of your system, some things might be actually fitting well, some other might not. Okay, so how it works? So now let's provide a simple implementation of our formula that we'll use for the boiling point estimate. And here's one way we could implement it. So in line 1, we define a lambda, a function that basically implements the formula above. And we use the context manager for a sanity check, for a unit test, in which the range block would be the injection of the constants. What we test is evaluation of this function. And then we assert both on the value and on the dimensionality, right? So we see that line 1 is in any way, not in any way special, right? This is what would go okay with SciPy, with Numba, with whatever. This is just a Python function. And what we use here, what we leverage, is the fact that a fundamental trait in physics is that units, dimensions, only originate from constants. The mathematical part of physics does not inherently contain units. The physical constants are the origin of units, right? So any physical formula only gets units after you put the constants there. So this approach maps the physics logics. We have the formula as it is, and then we inject the units, which can be either unit-aware objects or just plain floats for simulation. You can think of simulations, plotting, debugging, testing, different contexts that you might want with or without units. Okay, so here is the final answer to our question, what's the boiling point of water? Let me ask Camille also to post this snippet so you can play with it yourself. And let me quickly just go through the listing. Line 1 is actually something that is new in SciPy, the element-wise operations for root finders. So here we leverage the new logic in SciPy that it can perform the numerical optimization for a whole vector element-wise. So we import find root function from SciPy. And then we have 2 blocks. The first is with dimensional analysis disabled. Basically the simulation or the computation, the number crunching. And then the second block from line 10 till 17 is plotting. And besides testing, Pint is so useful for plotting because it automatically puts the labels on our axis. It can convert things, etc., right? So here, let me quickly go through. Line 3, we instantiate the context manager and we use the with statement for running lines 4 to 8 without the dimensional analysis. So we get the constants, we execute SciPy's find root, passing the function, our problem of inversion. So basically this, P atmospheric minus P equilibrium equals 0. So this is our problem to be solved. Okay, then line 5, this is a requirement of SciPy to provide a rough estimate, a bracket where to look for the root. So we give a range of temperatures that we know that the boiling happens in. And then we pass the argument in line 6 to our function, which is the range of pressures we want to know the boiling point for. We picked 1 atmosphere and 1/3 atmosphere. 1/3 of atmosphere is roughly the Mount Everest pressure. So 330 hectopascals up at the top of the mountain and 1,000 at the bottom. We assert finally that all roots are converged, and in lines 10 to 17, we do the plotting, but now with the constants catalog being unit aware. And you see that this helps us to get a plot where we also leveraged the unit conversion feature. So x-axis here is standard atmosphere. So on the right-hand end of the x-axis, we have 1 atmosphere, so roughly what is in this room. And we see that the boiling point is roughly 100 degrees Celsius, which is what we expect. We boil water at roughly 100 degrees. However, if we go left with the x-axis towards lower pressures, so basically hiking up a high mountain, we see that the red line in the plot lowers to the left, reaching boiling temperatures below 80 and further down, right? So this was meant just to be a kind of a real-life example. Of course, in reality, we try to use these for much more complex simulations. But the idea that we have the physics, the numerics, and the units somewhere in between is here. Questions? No questions. Okay, so a quick poll. Takeaways, sorry, before a quick poll. Takeaways. So basically, the first takeaway, or just kind of a reminder, is that it's worth to think physics when coding physics. And the fundamental thing in physics is that the units really only come from constants, and this is what we mapped to our Python code with the injection of the constants catalog, right? So this is the only thing that needs to be changed with running the code without any unit versus with units everywhere. So if all your constants are in the catalog, you have a guarantee that all operations will be unit aware, because the constants cannot get there from elsewhere. We think that potentially it's a useful design pattern, this injectable constants catalog. We suggested a context manager implementation, but of course there are other ways to switch. There are frameworks for dependency injection in Python, so you might just use your favorite framework. And the nice thing is that this solves both the interoperability with SciPy, but also the performance. So the both limitations that are quoted as limitations of Pint go away, because we make the whole calculations work with plain floats. So we are automatically solved in both the performance and interoperability aspects. So the third thing out of 4 we would like to present today is coupling Pint with Numba. Please raise your hand if you have used Numba in the last 2 years. I'm scared to ask you in the last month, because with the competitors, the use of Numba declines. But okay, so roughly half and half. So I will need to say just a bit about Numba. Maybe we can just open quickly Numba website. So Numba is a just-in-time compiler for Python. The slogan is Numba makes Python code fast. From maybe more developers' perspective, Numba provides a re-implementation of NumPy. Numba provides multi-threading. Numba provides just-in-time compilation of a subset, and this is very important, of Python syntax. So Numba is perfect if you have a bottleneck that is related with NumPy. Then Numba is the go-to solution, in my opinion, because it can easily be just used for a small part of your code where the performance of NumPy-related operations is too slow. And this can solve the problem by just-in-time compiling to native machine code of a single function or some set of functions. Okay, so can we use unit-aware function with JIT-compiled code? Right? We've just learned that unit-aware functions are perfect. We can get a lot of maintainability improvement from it, but we also need performance. So sometimes we need to resort to just-in-time compilation with Python. Let's try. Here is a minimal example, 7 lines. From Numba import JIT. The first line imports the just-in-time compiler. This is a function which can work as a decorator, or you can use it as a function. It compiles another function. So in line 3, we create a new function, pexJIT. This is a JIT-compiled version of our equilibrium pressure function, which is the JIT compiler function, which takes the result of the JIT compiler function with the original function passed as argument. Okay? And then we try, with dimensional analysis enabled, get the constants, and use the JIT compiled function. Doesn't work. What's the error? Actually, there are 2 errors in a way. So the error, the last 2 lines of the error, this is the error from Numba. It tells us that Numba does not support Pint. Or more precisely, cannot determine the type of Pint quantity, right? Because just-in-time compilation implies that we need to know the concrete type of every variable to make it produce a machine code. Numba does not feature built-in support for Pint, so it mentions that the first argument is a Pint quantity. But look, it also doesn't even support the basic Pythonic simple namespace, right? And this is not really I mean, it's not a bug or something to be solved. It's kind of the feature of Numba that this is used for NumPy-related number crunching. So it's not a general purpose just-in-time compiler of Python. It's a very specific tool for improving performance of NumPy-related or computational codes. So we need to somehow solve two problems. We need to strip units in a maintainable way, and we need to strip the simple namespace from our code. Okay, so the solution is not that long. Camilo, let me ask again to paste this on Jitsi. So first, instead of simple namespace, we'll use something that for a user is exactly the same. It's a named tuple. It's a built-in in Python, and Numba perfectly supports named tuples. So you can, from user perspective, the usage of simple namespace and named tuple is the same. Actually, if you think about it, our simple namespace is for a constants catalog. Constants are immutable by design, right? They are constant. And named tuple is also immutable type. So actually converting it to a named tuple in line 6 is a very meaningful thing because it actually expresses in the code our intention of storing a catalog of constants. It's immutable. So in a way, this is not really a trade-off. It's an improvement that we switched from simple namespace to a named tuple. And finally, the nice thing is that the whole design pattern of the injection of constants catalog not only solves the problem of coupling with SciPy, but it also solves the problem of coupling with Numba. Because if we use Numba inside the with dimensional analysis disabled context manager, we are good. Everything is float. So both errors go away. So quick recap, line 6 solves the problem of simple namespace not being supported by Numba. We convert it into named tuple. And line 3, execution of everything under the context manager that switches the true Pint unit catalog into a fake one, basically floats, solves the second problem. So, to summarize, we can reuse the same design pattern for the injectable constants catalog for interoperability with both SciPy and with Numba. And for the issue of lack of support for basically any complex collection object is not supported by Numba out of the box. You need to have typed dictionaries, typed lists, or tuples or named tuples. It's part of Numba story that you need to know the types. But actually, in our case, it's in fact an improvement because we express in the code the immutability of constants. And just to reiterate, the fact that physical units appear in physical operations, physical computations only through constants, it's kind of a DNA of coding physics. So we managed to use it this way. And probably from what we can read on Stack Overflow, etc., it seems that maybe you're creating a prompt for this kind of problems. It's nice to start the prompt with saying that we have a problem where all the units are in the constants. Dear chat, please tell me how to couple SciPy plus Pint. Because with this as a starting point, the solutions are much more useful than just asking for coupling SciPy with Pint, because what you get is basically unmaintainable. It works, but it's unmaintainable. Okay, So that would be it. Questions for the number part? I hope this was useful both for number users or for those who are new to number. And our last part of the tutorial is number and MPI. And let me ask Kamil to cover the fourth chapter. There's a question. Uh-huh. Well, I would say that the idea applies equally because it applies to any language, any technology. In JAX, the arrays are immutable. So there are some, I would expect there will be some trickery into adapting this pattern to JAX because with the immutability of arrays, well, okay, so I haven't tried. So basically, this is my answer. The pattern should apply because it applies to other languages as well. We have tried it with Julia, we have tried it with Python, we have tried it with C++. So we have 3 concrete examples where the same pattern works. For C++, we use the boost units. For Julia, we used the units.jl. For Python, we use Pint. And the same pattern, just switching the unit-aware catalog versus unit void catalog works. I expect this should work with JAX, but I also expect that since JAX introduces a lot of new ways of coding with the immutability of arrays, with the assignment operators that indicate the data dependencies, etc., it might have some caveats. But in principle, the concept is not in any way limited to Numba or Python. Thank you. Thank you, and it's a very important point that actually NumPy by itself violates a bit the semantics of Python, right? We, like with the, even with the assignment operator, you can assign or the, if you start here and you notice the difference, and then if you try to play with it, we'll soon notice that the way NumPy interprets how to call it? Exactly. Okay. So let me show what I had in mind. Maybe actually we'll find an answer to a question. So these are our slides, and this is Numba here, and there is a fishy this. Let me comment this out and run everything. So maybe let's. So actually, the code that we've shown to you with Python, with NumPy 2.0 produces a small warning that is exactly, I think, related to the comment here. So we need a. Exactly. Right. Okay, ad hoc stuff is not good. I have the screen here. Why it did not work? Name pint is not defined. Sure. So you can share on Jitsi? Okay. This is much better. Yeah, so, but in principle, the key takeaway here is that immutability of a tuple or of a named tuple, which contains a NumPy array, does not mean that the data of the array is immutable. And that's a very valid point. And this is actually what the JAX question is relevant, because JAX introduced completely different approach to array operations in terms of ensuring immutability, ensuring data dependent, or understanding data dependencies, right? With NumPy, it's tricky. With NumPy, you can easily produce a statement which will work differently if it's run from left to right or right to left. Because if you look at a neighboring element of an array, like in finite differences, you look always to the right neighbor, let's say. You can code it in object-oriented manner in NumPy. But depending on if it's implemented from left to right or right to left, it will give another result. And this is part of the story that actually the operations in NumPy do not express the whole logic. And JAX actually does it with the immutability of arrays, so you can actually, the just-in-time compiler can really, truly infer the data dependencies between arguments, operands, etc. So this kind of differences appear. This was an ad hoc thing, so let's go back to the story because Kamil has a final chapter to present, and we can go back in the questions. There will be time for questions. So, Camilo.
So now we basically covered all the main things we wanted to show you. So the pint, SciPy, and Number. And now we are going a little bit further with the MPI. So another question is, does anybody use MPI or try to use MPI and Number at once?
There was one hand for MPI. Okay, first MPI. 5, 6, 7, okay. And MPI plus Number.
Okay, so we will try to do it here. So yeah. Normal step, we want to improve our code, our performance. So we will use we want to use the MPI. For Python, we have the MPI for Py package, which allows us to use MPI in the Python code. And yeah, we tried out and we have a simple example here. So what we're trying to do here, yeah, we are using NumPy, Number, and MPI for Py, and that's all for now. So we are defining a function ping pong, which will just send us data from worker 0 to 1, and the worker 1 will receive the data, and we want to run it. This function is covered by JIT. So we see that we get an error because Number does not support MPI for Py, and that's basically because of MPI for Py. It's almost pure Python package, so it's like an object-oriented package, while Number isn't. It isn't. So it's normal that MPI for Py is not supported by Number here. So basically, if you want to do anything with those functions, we will get an error because we could use to bypass that using the object mode, right? But normally it wouldn't work like this. So what's the solution here? The solution is to use the Number MPI package, which is also one of the package in our team we are developing. And here, what we are going to do is just we are removing MPA4Pi package here and replacing it with Numba MPI. So we still have the same function, digitable function, but here we are using the Numba MPI version of send, receive, and rank. And as you can see here, executing it from the terminal using the MPI exec, we see that we correctly send data, which is from rank 0 to rank 1, and we get the array. Also, the first example here wasn't even, we didn't even need to use the MPI exec because only at the stage of trying to Numba to compile this function, it crashes. So here we have a full example that it does work. So this is basically another step of this, that since we can now glue Pint and SciPy, we can also use Numba. So with this, we can also use whole code before and run it on multiple workers. So as the title of this tutorial is about the high performance, we probably covered a lot of things here to show you that it could work as a one code or one thing, not to divide it. And so basically this is everything we had to show you today. So we have two QR codes here. One refers to the preprint of the paper we talked at the beginning, and the second one to our repository on GitHub from Numba MPI. So if anyone wants to leave some feedback, or do you have any comments, questions about how does it connect all together, or anything more, we'll be happy to talk about this. So I think
thank you
that's all.
for your attention, and we are very much open to questions and further discussion. Maybe one follow-up to the question about the mutability of arrays. If I understand correctly, the way Numba violates the NumPy logic is that it treats any global from the perspective of anything out of scope of a JITed function is assumed to be constant. So actually the LLVM under the hood can assume that the constants of some array are immutable just because they are defined out of scope. So this is another example where the immutability would be useful thing to be expressed, and I guess this is why JAX introduced this concept that just any array is immutable, period. But Numba actually does it in a way that if you pass it as argument, it will assume it's variable. If you use it as a global or just one scope level up, it's assumed to be constant for optimization or for whatever, I guess also for just tracking what happens then. But this is another way where actually the logic of one package kind of conflicts with the logic of a type from another package, array in this case. Which is impossible. Yeah. Yeah. Thank you. And so let me also clarify that the way we use Pint with NumPy is always to have an array, and the unit applies to the whole array, not to the elements. So actually, in a way, it's also metadata. So, yeah. Yeah, NumPy is still using under the hood a contiguous slab of memory with typical array operations. And the checks for units only happen at the operator interpretation level. So it's NumPy still does what it usually does. Exactly, yeah. Looking forward to it. And actually, even the function that we use, this element-wise find root, also handles array API already. So inside the docs, you can see that GPUs, etc. It didn't. But maybe, well, I mean, definitely the way SciPy evolves towards abstracting away the array layer is probably a door opener to solving such things in a much more elegant way. So that's a very valid comment. Other questions, feedback, comments, your experience with similar stuff? You can find us, let me go back to the first slide. Second slide. So, OpenAtmos KRK, GitHub.io, that's our group website. You'll find a list of all students involved in what we do and a list of all packages that we maintain. These mostly are related with atmospheric modeling, but like with NumPy MPI, we have packages also that are very general purpose in use. NumPy MPI is a dependency of two PDE solvers external to our team, so it kind of works for also external users. And if you ever happen to need NumPy with MPI, that's the way to use it. It's a very thin wrapper around the C MPI interface without any dependencies, so we use C types for interoperation. It just glues together MPI C library with NumPy. Thank you so much for joining, and enjoy the rest of the conference. And we have NumPy MPI stickers, if anyone would dare to stick it somewhere. Thank you. So, stickers, stickers, stickers. I hope, but they are in HTML, so what's the best?
You can just paste the HTML file in Discord.
But the question is if it's self-containing zip,
No.
just pay. Otherwise, I think make a zip. Make a zip of the whole folder. If it's below 10 megabytes, it will fit in the Discord as a zip.
Probably 100 kilobytes.
Images could be a problem, but I don't find it.
No, there. I mean, all the. Anyhow, yeah, we'll do it. Yeah, to Discord.
I think yes, it's best.
I have to. If you say